All right, let's recall where we were before spring break. We had this example system that's somewhat similar to your system you're doing for your project, maybe a little bit simpler. But we have this Segway system where we have this wheeled vehicle that should be self-balancing and can move along the ground. In this case, the ground is not flat, it's sloped at some angle beta. The lean of the Segway was this angle theta. The rotation, the amount that the wheel has rotated is something we call phi. And we derived equations of motion for this thing. So it took us a little while to do it, but in the end we got our equations of motion. And then what we did is we created a Simulink model for the system. I happen to have the Simulink model up here, so what we have here, this right here, I think this is the heart of the model right here. It's the integrator. So going into, I'll say it this way, going out of the integrator is the state. Going into the integrator is the derivative of the state. And that's, of course, the relationship between the input and output of an integral, right? The output is the integral of the input. Or you can say it backwards, the input is the derivative of the output, which is what we have. The important point to remember is that our system can be expressed mathematically as this system of first order differential equations. X dot is equal to f of x. In this case, we don't want our system just to depend upon x, but also depend upon a control input. So it also depends upon something we call u. So here, x, that's our state, and x in the case of the Segway is the collection theta dot, phi, and phi dot. Right, so in the case of the Segway, the state is four-dimensional. You get the lean angle and the rotation angle of the wheel and their derivatives. The u is the control input, right? It's the way that we, the user or the control designer, can access the dynamics of the system, right? The way we can influence the dynamics of the system. In this case, u is the torque from the motor, right? This is the motor that's turning the wheel relative to the body. This is something that we have control of as the control engineer. And it fits into the system sort of mathematically or symbolically right there. And again, earlier in the semester, we derived these equations, right? When we applied Newton's laws of motion, we get these equations right here, which essentially gives us these angular accelerations for the two parts of the body, which depend upon this motor torque, the tau. I've got it sideways for you. Hope you can turn your head. And then to recap, what we did is we constructed a Simulink model. Again, coming out of the integrator is the state. There's the state right there. Going into the integrator is the derivative of the state. So the state comes out here, we swing it, we pull it back around, and we connect the state up with the input, the tau. That's the motor torque. We set the motor torque to 0 for now. But here's the state and the control input, the tau, right? There's the state and the control input that goes into a function which calculates the time derivative of the state. Let's bring it back up. So here's the state and the control input. They go into this function, and the function calculates what is the time derivative of the state, which goes back to the integrator. Now this function, which is the time derivative of the state, we wrote a MATLAB script for this, or I should say a MATLAB function. The function was called RHS Segway Slope. It took an input, and its whole purpose was to create the derivative of the state. So we essentially calculated those equations for us. We had this matrix that we had to essentially invert, solve for the unknowns. So the derivative of the state, I'm just reviewing very quickly what went into this. Of course, you can ask me questions if you find this confusing at all. Now here we have our Simulink model again. There's that interpreted MATLAB function. We just double click on that. It has RHS Segway Slope in there. So it's calling this function, this custom user function that we defined, and it's putting it in the loop there. All right, so also, as I said, coming out of the integrator was the state, and we've got a scope that pulls the first state off, right? Remember, there's four states. The first one was the theta, second one was theta dot, then phi, and then phi dots. So on this scope right here, we are ready to, as soon as it runs, we're ready to plot the theta, the angle at which the body of the Segway is leaning. So that's ready to go. So let's run this thing and remember what we got. So I click run here and it simulates the system. So we started off with an angle of 0. So remember, we're looking at theta here. On the horizontal axis is time. So we're running this simulation for, it looks like 30 seconds. And it looks as though theta starts off at 0. So the body of my Segway is completely upright. In fact, I can double click on the integrator. Yeah, indeed. So there's my state dot, phi, excuse me, my theta dot, phi dot, all at 0 to begin with. So the pendulum, or the Segway, is completely upright. We see it starting there at 0, and then it falls over sort of on the, it goes negative, so it falls over on the uphill side of the upright, and it looks as though it falls through the ground. I guess that's not really physical, but we don't have the impact with the ground in our mathematical model, so it swings all the way down through the ground and comes back up upright again, and swings back down and goes back up upright again. So that's what's happening with the theta dynamics. And the phi, you can probably imagine this thing's rolling down the hill, although I won't show it right here. So what we have is an unstable system. It's not even at the equilibrium. It's just sort of falling over, as you would expect if you have a Segway on the hill and you're not applying any motor torque to the wheels. And that's our very, very quick review of the Simulink model for the Segway. Next thing we'll do is we will apply a motor torque and a special lean angle at which we hopefully this system will be at equilibrium. We'll hopefully find an equilibrium here.